Hello everyone, this video is about Cholesky's LU decomposition. In a previous video, we saw that the constraint for this method is that the lower triangular matrix is equal to the transpose of the upper triangular matrix, which leads to this LU decomposition. Here we choose the latter form. The product of the lower and the upper triangular matrices is the matrix on the right hand side. As we can see, this is a symmetric matrix. And this explains the first limitation of Cholesky's decomposition method, that is, it requires A to be a symmetric matrix. The good thing is that because of the symmetry of this matrix, we only have to solve 6 equations, that is, 3 diagonal and 3 non-diagonal elements. As we can see, this process involves taking square roots for some elements. The square roots of negative numbers can be avoided only if A is positive definite, which is the second limitation of Cholesky's decomposition. The last 2 steps are the same as before, that is forward and backward substitutions. To implement this, we write a Cholesky decomposition function which takes the coefficient matrix and the output vector as inputs. On line 257, we check the first requirement. If the matrix is not symmetric, the function returns the statement A is not a symmetric matrix. So we can choose any of the methods described in the previous video, or any other alternate method. If it is symmetric, we check the second requirement, and if that is met, we move on to the calculation of 6 elements of the lower triangular matrix. On line 265, we start the loop and only check the lower triangular elements. If the row index is equal to the column index, we update the diagonal element on line 269. Else, we update the off-diagonal element. And since the matrix is symmetric, we update the corresponding entry in the upper triangular side. This is followed by the forward and backward substitution steps. These are the same codes as described before. Forward substitution as used in the Crout's method and backward substitution as used in the Doolittle's method. I just changed the name to be more clear here. Now, if we apply this to our example curve fitting problem, we are told that A is not a symmetric matrix. So we can use any of the previously described method to get the solution. To demonstrate whether the code works, we try to solve another system of linear equations where the coefficient matrix passes the 2 requirements. And we get the correct solution, which suggests x1, x2 and x3 are all equal to 1, which we can verify by placing these values into the equations and checking whether the right hand side equals the left hand side. In the next video, we will discuss the Gauss-Seidel method from the iterative methods class. Thanks for watching. I hope you liked this video. Please subscribe and see you in the next video.